Hi, I'm Dyson Guna. I'm going to take you through the series of videos for fluid mechanics and 5 for the native programs in South Africa. Fluid mechanics and 5 has 11 modules. I'm going to take you through each of these modules in a series of videos. Today, we're going to discuss the properties of fluids. We're going to take each property separately. I'll show you how to go through the calculations. In as much as I'll be focusing on the calculations, make sure that you also study the theory, like the definitions and all the related principles that go with each module. When we look at the properties, we have several of them. There is viscosity, surface tension, we have compressibility, and also the densities and other properties that go with the fluids. But for this video, I'm going to focus on the viscosity. Viscosity, as it is defined, is the measure of the internal friction of the fluid. And this is divided into two types. There is the dynamic viscosity and the kinematic viscosity. Dynamic viscosity is defined as the resistance of the movement of one layer of fluid over another. As fluid flows, then the different layers of the fluid slide over each other. So that is the dynamic viscosity. Meanwhile, the kinematic viscosity is the ratio between the dynamic viscosity and the density of the fluid. Let's go to the calculations of the viscous force and the power loss due to the viscous force. In as much as lubrication or lubricants are needed to reduce power loss in machines, it also costs a small amount of power loss. So that is what we're going to focus on in these calculations. The power loss is due to the stickiness of the fluid as the machine parts or different components move over each other. Let's take a quick look at these few calculations here. We have different types of questions related to the viscous force. First, we have the ones related to the general bearings and rotating shafts. Secondly, we have non-rotating shafts or pistons, where we have a piston that is moving to and fro inside a cylinder. We also have the third type of questions, where we have sliding between two surfaces, where we have a component, like in this case a machine, that slides down the slope. Here, that is on a flat plate. Let's take a quick look at the first type of question. That is the general bearings and rotating shafts. The question here says a shaft of 80 millimeters diameter revolves concentrically in a fixed bearing of 80.5 millimeters in diameter, and its length is 100 millimeters. The annular space is full of oil, and it has been found that the torque of 1,85 Newton meter is required to drive the shaft at 1,000 revs per minute. Calculate the following. All right, the first one is the absolute coefficient of viscosity. Here, I'll take you through the problem solving steps that you need to take. And these you need to do also in the exam to make sure that you don't do unnecessary calculations. First, before you do your calculations, you must write down the given data, all the data that is given here. Write it down. All right, let's go through that. We are given the shaft diameter, which is, all right, we'll say the given data here. I'll just write it there. We say, okay, our given data, first is the diameter of the shaft, which will represent by a small d of 80 millimeters. Then the diameter, the internal diameter of the bearing, the general bearing, which is 80.5 millimeters, and the length of the bearing, that is the width of the bearing, is 100 millimeters. Then the torque that is required to drive this shaft is 1.85 Newton meter. And lastly, the shaft will rotate at the speed of the rotational speed of 1000 revs per minute. All right, now the first question is we must calculate the absolute coefficient of viscosity. So we must look for the formula that involves the absolute coefficient of viscosity that we're going to use based on this given information. All right, we have the formula for the viscous force. The viscous force, which is the absolute coefficient of viscosity multiplied by the contact area multiplied by the velocity, the peripheral velocity of the shaft. This over the space between the shaft and the bearing, which is the shaft, which is the clearance. This is the space that is filled with the lubricant. All right, so after writing down the formula, then we have to derive this formula so that we make the coefficient of viscosity the subject of the formula. So this would be it's F multiplied by T. If we manipulate this formula, we'll have F multiplied by T over area times V. Now, after manipulating this formula, we ask ourselves, do we have the force? If the force is not directly given in this data, then we must look for the information that will help us to calculate the force. All right, we have the torque there. We also have the shaft diameter. We know that torque is the same as the force multiplied by the radius. So to calculate the force, we manipulate this. We'll say, okay, this is torque divided by the radius. Our torque is 1.85 over the radius, half of this diameter, or the diameter of the shaft, which in meters will be 0.04 meters. So when we calculate this, we find our answer to be 46.25 newtons. This is the force. All right, now we've calculated that force there. We have the force towards calculating the absolute coefficient of viscosity. All right, we have T, the clearance between the shaft and the bearing is not directly given, but we can calculate it. That is from this sketch here, this space here, this is the shaft, and the blue part represents the clearance. This is the diameter of the shaft, is the diameter of the shaft, and that is the clearance, is the clearance. Meanwhile, the whole of this is the diameter, the internal diameter of the bearing. When you look at this, you'll see that the big D, the internal diameter of the bearing, is the same as is the same as the sum of the shaft diameter plus 2 times T. That is T plus D. They give us the big D. So to find T in this case, we'll say is the big D minus the small d over 2. So we use this formula to find the shaft, the clearance between these two. All right, the clearance T is the big D minus the small d over 2. This is 0.0805 minus 0.08. Then we divide this by 2. Make sure you don't round off here, because if you round off, you're going to miss your answer by a certain margin. So because we are dealing with tight tolerances here, it's good. I always advise that you write your answer in engineering notation. So this will be 250 multiplied by 10 to the power negative 6 meters. Is in meters. All right. Now in that formula, that manipulated formula, now we have T. The next step, we need to calculate we must calculate the area. In calculating the area, we need to take note that as this shaft rotates here, this film of lubricant will also be rotating with the shaft. So in this case, we need to consider that is this shaft, this lubricant that is rotating as well. So we need to take the mean diameter. We need to use the mean diameter in this case in calculating the contact area between the shaft and the contact area of the shaft. So we'll say area is equals to, in this case, the contact area. Here I need to caution. Students, in most cases, they love the formula A is equals to, once they have a circle, they'll say area is pi over 4 d squared. In this case, this formula is not correct because we are not lubricating the cross-sectional, the cross-sectional area of the shaft, but the outside of the shaft. So in this case, we need to consider the circumference of the shaft, but going through the mean diameter. So the circumference of the shaft will be pi d, mean. So to find the area, we must use this pi d mean multiplied by the length of the shaft or the width of the bearing, not the length of the shaft, but the width of the bearing, which is represented by this length of the bearing, the length of the bearing. So we'll say area in this case is pi multiplied by d mean will be the sum of 0.0805 plus 0.08. Then we divide this by 2. Then we multiply by the length, which is 0.1. So this here represents the mean diameter. So when we calculate, we'll find, sorry, my space is not enough. So we'll find the area to be 25, that's 25,211 times 10 to the power -3 square meters. This is our area. Now in that formula, we have the area. The last thing that we need to calculate is the velocity. Given this information, V is equals to pi dn over 60. Here we use the diameter of the shaft. So it would be 0.08 times the rotational speed. It's 1000. Then we divide this by 60. When we punch our calculator, we get this to be 4,189 meters per second. Now we've calculated all the information we need to find the coefficient, the absolute coefficient of viscosity. So we go back there and then substitute. The force is 46,25 multiplied by the thickness or the clearance divided by the area, which is 25, comma 211 multiplied by 10 to the power -3 multiplied by the velocity of 4.189. This is equals to 0.109 Pascal second. This is our coefficient of viscosity, which is also referred to. This absolute coefficient of viscosity is the same as the dynamic viscosity. So if they say calculate the dynamic viscosity, you must know that is the same as the absolute coefficient of viscosity. The next question is the power loss due to the viscous forces. The power loss due to the viscous forces. In this case, because we have the velocity, we have the rotational speed and also the torque. We use the formula power is equals to 2 pi nt over 60. So when we substitute, is 2 pi multiplied by 1000 multiplied by the top of 1.85 over 60. This gives the power of, let me calculate, this 2 times pi times 1000 times 1.85 divided by 60. So it's 193, 732 watts. This is the power loss. Then we come to the third question, which says, calculate the critical velocity. Calculate the critical velocity of this oil when it flows in a pipe of 75 millimeters in diameter. If the critical Reynolds number is 2,300 and the density of the oil is 780. So in calculating this, we write down the formula for the Reynolds number. Re is equals to the density of the fluid multiplied by the diameter of the pipe multiplied by the flow velocity, all this over the coefficient of velocity. What we are looking for is the critical speed. It's not the same speed as the one we've calculated there, because this is the peripheral velocity of the shaft when the shaft is rotating. So if it was rolling on the ground, it would be moving at this speed. This is the flow velocity of the oil when it's now flowing in a pipe. When we manipulate this formula, we say V is equals to Re multiplied by the coefficient of viscosity over the density multiplied by D. We've been given that our Reynolds number is 2,300. We multiply this by the coefficient of viscosity that we've calculated is 0.109. All this over, we've been given the diameter of the pipe, which is 0.075 multiplied by the density of the fluid is 780 kilograms per cubic meters. When we calculate, it gives us 4.457 meters per second. That's it. Let's quickly move to the second type of question, which normally comes in this module. That is when you are required to calculate the viscous force. It can be the first type, which is the rotating shaft and bearings, or the non-rotating shaft and piston. When going through these questions, first thing, you write down the given data. So, all right, the given data is the piston diameter, the D, is 120 millimeters, and the length of the shaft, of the piston, it's 150 millimeters. This moves up and down in a reciprocating motion inside the cylinder with the internal diameter. The internal diameter of the cylinder is 120,2 millimeters. And it's moving at the speed of 1,2 meters per second. Determine the resistance or the viscous force caused by the oil with a coefficient of viscosity of 0.3 Pascal second. That completely fills the gap between the piston and the cylinder. All right, we have our piston that is moving up and down there. It's moving up and down. And we have the lubricant there. Lubricant that fills the space between the shaft and the bearing. And the piston. All right. Here, to calculate the viscous resistance, so we must calculate the viscous resistance. In other words, we must calculate the force. To calculate our force here, we write down the formula is the coefficient of viscosity multiplied by the area multiplied by V over T. In this case, let's see. In this case, we say, what information do we have? The coefficient of viscosity is given, so we need to calculate the area. V is also given, so we must calculate T. How do we calculate the area? Unlike with the rotating shafts, here you use the diameter of the piston. You don't use the mean diameter. You use the diameter of the piston. Because this is it's a sliding motion, it's a linear motion. There's no rotation here. So you consider the diameter of the piston. All right, so our area will be, our contact area is pi multiplied by 0.12 multiplied by the length of the piston is 0.15. When we punch our calculator, we find the answer to be 56,547 multiplied by 10 to the power -3. This square meters. So we have the area now. So we go to T, which is the clearance between the piston and the cylinder. This is the diameter of the cylinder minus the diameter of the piston over 2, which is 0.12. I think it's 1202 minus, don't round this off, write it as it is. And after finding the answer, don't round it off. It's better you take your answer to either engineering notation or scientific notation. So this will be 1 times 10 to the power -4 meters. This is our T. So now that we have all the information required to calculate the viscous resistance or the viscous force, Then we substitute. This is 0.3 multiplied by the area, which is 56,547 times 10 to the power -3. This multiplied by the speed or the velocity of 1.2 over t, which is 1 multiplied by 10 to the power -4. When we calculate here, we get our viscous force to be 203.575 newtons. There we are. We've calculated the viscous resistance. Now let's go to the last type of question, where we have a sliding plate, or that is, we have a machine or just any part that is sliding over a flat plate. In this case, when we have this on a slope, sliding on a slope, the weight of this body will act vertically down and is given by its mass times the gravitational acceleration. This mass has its components, which is going down the slope, and another one is at 90 degrees to the slope. From what you learned in Euclidean geometry, you know that by now, you know that the angle that is formed between the weight and its component that is at 90 degrees to the slope is the same as the angle that is formed between the slope and the horizontal. All right, this component here is given as W, the cos of the angle, and that one there is W, the sine of the angle of the slope. So what you need to know is, as this force here, the W sine, is moving this down the slope, will have the resistance which acts against the motion, the direction of the motion. Will have that resistance there, or the resisting force. So the question that we've been given here, it says, a machine with a mass of 250 kilograms rests on a flat plate with a contact area, with a contact of 500 millimeters by 600 millimeters. The plate is then tilted until it reaches an angle of 8 degrees. In other words, this angle here is now not 18, it's 8 degrees. It's 8 degrees to the horizontal. Determine the maximum speed at which the machine will slide down the slope. If the machine and the plate surfaces are separated by a 1.5 millimeter film of lubricant. In other words, this is our T. T is equals to 1.5 millimeters film of lubricant with the coefficient of viscosity of 0.3 Pascal second. All right, we have the mass as per norm, right? The mass of the machine is 250 kilograms. The area is 500 by 600. So we have to change this to meters. In meters, our area will be 0.5 times 0.6. So this gives to give us 0.5 times 0.6. It gives 0.3. 0.3 square meters. All right. So in order to calculate the velocity, we write down the formula for the viscous resistance, which is coefficient of viscosity multiplied by the contact area multiplied by V over T. We are looking for V. Then we rewrite this formula as F times T over area times V. All right. Do we have the force? No. So our force, the resistance from Newton's third law, this resisting force here, the force that is going up the slope is the same as the force going down the slope. In other words, we use the Newton's third law of action and reaction. So our viscous resistance here, which is the force that we are looking for, is the same as the W sine theta. All right, which is 250 kilograms times 9.81 times the sine of 8 degrees. This gives 341,322 newtons. So we have the force there. T is given. The area we have, I'm sorry, this is area multiplied by the coefficient of viscosity. So we say this is, when we substitute, say 341,322 multiplied by 1,5 times 10 to the power negative 3. I've converted this to meters. And then we divide this by the area, which is 0,3 times the coefficient of viscosity, which is 0,3. All right, when we calculate here, we get our maximum speed or maximum velocity to be 5,689 meters per second. That's it. So just use the approach that I've given you to assist you in your examination preparations. Let's meet in the next video. Thank you.